Hi, in this video we're going to have a look at transformations of the tangent function. They're not quite as complicated as they are for sine and cosine, so they're not too tricksy in a way. You might remember that the two main transformations we had a look at for sine and cosine were amplitude, which is the distance between the middle of the graph and the maximum or minimum, and the period. And they're effectively dilations effects. Well, in the tan graph, let's have a look at the dilation in parallel to the y-axis. So that means looking at the value of a. When we increase, just to make it clear, that's what we're talking about here, multiplying tan by a, big A. So as I increase a, all we're doing is we're stretching every single point away from the x-axis. So it's stretching in the direction of the y-axis. So that gives us a steeper graph. And similarly, if I go to 0.5, it's just flattening. So there's a equals 1. And as I go to 0.5, it's flattening, flattening, flattening. And that's all it does. It still retains the basic shape. It still goes to infinity as it gets to the asymptotes, or from negative infinity up to 0 from the other side of the asymptote, but it ultimately keeps the same shape. And for that reason, it's not really considered a dilation that we need to worry about too much when graphing. And you certainly don't need to worry about it this year. We do worry about reflections, and reflections do what you'd think, I think, which is here's a regular base tan graph, and if I make it a equals -1, then it's the same graph but flipped. So instead of going up like this, it's going down, and then it climbs from infinity down to 0 and then goes from 0 to negative infinity. So everything's flipped. It's a flipped graph, and that's all you have to worry about in terms of that particular transformation. So reflections are in, dilations of vertical dilations are out. Horizontal dilations are in, so you can see you've got a tan nx because n does affect the period. So it should behave as you should expect by now. So if I make n equal to 2, like so, I've run out of asymptote lines, but you can see that we've effectively shrunk our graph, because if I make n equal to 2, then we're speeding through the values of tan a lot quicker. So we've got an asymptote at pi on 4, and then 3 pi on 4, and so on. We've got this graph escalating quite quickly here, and then coming from negative infinity back to 0 here. So instead of being a period of pi, it's now a period of pi on 2. Similarly, if I go n equals a half, we've got a stretching effect instead, because that's effectively slowing down our going through the tan values here. So instead of an asymptote at pi, we've got an asymptote, at pi on 2, we've got an asymptote at pi. We've now got the graph completing one period, and then down here and then across at 2 pi. So making n equal to a half has doubled the period length to 2 pi. Okay, so what does that mean in practice? In practice, we don't worry about amplitude. We simply say the period is equal to pi on n. I should say this is y equals tan of nx. No a in front of the tan because it doesn't have enough of an effect to worry about this year at least. So the period is pi divided by n. The asymptotes are given by looking at what the equation. Well, I'll show you what it looks like on the information sheet. It's probably easiest. If you look at the information sheet, you can see it says solve nx equals pi on 2. Okay, that gives you your first asymptote, and then you can do the rest. So for y equals tan nx, period equals pi on n, and the asymptotes will be given by nx equals pi on 2. That's the base asymptote start. And now we'll solve for n, so we would have the new asymptote as being x equals pi on 2n for the first one, and then you keep on going up in that. You keep on going up by that many. Okay, so let's have a look at an example to make it all nice and clear for you. So the example I've given you is y equals negative tan 2x. So let's have a look at the asymptotes first. So we're going to solve 2x equals pi on 2. So that gives us x equals pi on 4, like so. So we're going to have an asymptote every pi on 4. And the period is going to be pi over n, which is 2. So the period is pi over 2. Okay, and you can see by our axes here, we're going to go up all the way up to pi for this one. So I will need to have an asymptote at pi on 4, which will be the middle here. And then I'll have to have an asymptote on the other side as well, like so. Next thing to consider is that it says negative tan 2x, so I'm going to have to draw it as a reflection. Make sure you don't forget that. So I draw my line in, like so. So it's the reverse of what it was. And then it's going to come back to the middle, like so. And then off to infinity again. And then it's going to return like so. And that's the graph done. I just wanted to show you on Desmos, it does reflect what we just drew. So we've got a equals -1, i.e. it's just a reflection, and n equals 2, and you can see we've got going down here and looping through, and then finally 1 going there. Okay, so that's how you solve that problem. The next one is just what happens if I've got a graph and I need to work out the equation. So here we go with that one, find the function. So we just need to work out the period and then need to determine if it's a reflection or not. Just as easy as that, I think. So the main problem I find that students do is that they just want to always put the period as 2 pi over whatever. And that's a problem because you end up then having double the number that you need to. Let's look very carefully. Where does it start repeating here? So we've got going from 0 up to infinity, and then going from negative infinity back to 0, 3 pi. So the period is 3 pi, like so, and 3 pi is equal to pi, the original, the base the base period, over n, the value we're trying to work out. Now we just need to solve for n. So I'm going to multiply both sides by n, and I get 3n pi equals pi. And then I'm going to divide both sides by 3 pi. I get n is equal to pi on 3 pi, which is equal to 1/3. So n is equal to 1/3. And so we can say, therefore, y is equal to, is it reflected? No, it's not. So it's y is equal to tan 1/3 x, done. Or you can write that as y equals tan of x on 3. These are equivalent. 1/3 of x is the same as x over 3. You could, if you wanted to, use the asymptote instead. If you can see an entire graph, there's no way I would do anything other than what I've done. But let's just say you were only given part of the graph and you were told that the asymptote is at 3 pi on 2. You could use that fact. I mean, you've got it on your information sheet here, is that the first asymptote is solve nx equals pi on 2. So you could work that, you could use that in order to figure it out. So I'll switch back over to this. So I could go pi on 2n is equal to 3 pi over 2. So I got 3 pi over 2 from this, my first asymptote, and you can see over here that effectively by just rearranging this statement, I get pi over 2n here. With that done, I can now solve for n effectively. So I can say, for example, multiply both sides by 2, and I get pi over n, because 2's cancel out, equals 3 pi. I could then multiply both sides by n. I get pi is equal to 3 pi times n. And I could divide both sides by 3 pi. And I would get pi on 3 pi is equal to n. cancel out the pi's, and I get n equals 1/3. So it's the same value. As you can see, though, there's a lot more fraction work happening here. I wouldn't do it unless I was absolutely forced to. It's much easier to do this. Okay, that's it for the examples. Have a go at the textbook work from the learning schedule.